Hello and welcome to our class. Today we are going to discuss one problem of optimization, the fastest parts of driving. Suppose you are driving through a desert and a grassland. There is no specific route for you, and you are going to determine a fastest path. Now let's see this example. You begin with the point A in the desert and are going to point B in the grassland. The line L is the intersection between the desert and the grassland. Suppose the average speed in the desert is V1, in the grassland is V2. The distance between the point A and the line L is H1. The distance between the point B and the line L is H2. Question is, to find the fastest way between the point A and B. Now first, let's draw the picture of this. Now let's see this picture. So this is the point A, this is the point B, and this is the line L, and suppose the length of CD is little l, and the length of CM is x. The length of MD is L minus x. And this angle is θ1, and this angle is θ2. The question is to find the point M to determine the fastest way. So first we need to find the time function. And the time function contains two parts. The first part is from A to the intersection. The second part from B to the intersection. And we find them one by one. So the first part is square root of h1 squared plus x squared over v1. Second part is h2 squared plus l minus x squared over v2 by Pythagorean theorem. Then, after we finding the time, we can take the derivative. So we find the derivative one by one. Then, using the fact that at the minimum value for dt dx should be equal to 0. I mean the derivative should be equal to 0. So we have that the fastest path from A to B must satisfy that the x over v1 times square root of h1 squared plus x squared equals l minus x over v2 square root of h2 squared plus l minus x squared. Now, we can insert in the following angles that x over square root of h1 squared plus x squared equals sin θ1. Likewise, we have that part equals sin θ2. So, we can get that the path that the car travels must satisfy that sin θ1 over v1 equals sin θ2 over v2. Well, if you travel across the different landforms, you will find your fastest path by this law. Actually, the effect of refraction can also be explained by using the analogy of a car moving across the different roads. When light travels from one medium to another, it generally bends or refracts, such as here, a shovel in the water looks like Band-Aid. This is because refraction. Now let's discuss the law of refraction. The law of refraction gives us a way of predicting the amount of bend. This law is also known as Snell's law, named for Wilbrod Snell, who discovered the law in 1621. Like with reflection, the refraction also involves angles that the incident ray and the refracted ray makes with the normal to the surface at the point of refraction. Unlike reflection, refraction also depends on the media through which the light rays are traveling. Snell's law is given in the following picture. From this picture, we can see that the law is sine theta 1 over V1 equals sine theta 2 over V2. It's similar with our car traveling problem. In Leibniz 1684 paper, a new method for maxima and minima as well as tangents, which is impeded neither by fractional nor by irrational quantities, and a remarkable type of calculus for this. It's a very long name paper. Leibniz also provided applications of his calculus to prove its worth. As an example, he derived Snell's law of refraction from his calculus rules. Given that light travels through air at the speed of v1 and travels through water at the speed of v2, the problem is to find the fastest path from point A to point B. Now let's see this figure. According to Fermat's principle of least time, Leibniz found the fastest path is the one that light will travel. By the same method we discussed in the problem of car moving across the different roads, Leibniz proved the law of refraction. Alright, we found the fastest path of driving through different landforms and the proof of the law of refraction. In the following class, we're going to study the Brake-Histow problem, which is a fantastic curve. I'm looking forward to seeing you next class. That's all for this section. Thank you.